We've spoken about quantum entanglement and its many implications on the nature of reality at some length now, but what we're going to do now is talk about some things that we can actually do with it, because quantum entanglement is one of the core features of quantum mechanics that really enables the entire field of quantum information. This video is going to focus on quantum cryptography because I think it's the easiest to explain in a relatively simple way. Nonetheless, you should bear in mind that everything that we do here is really the most basic of the most basic elements of quantum cryptography and quantum information in general. One of the oldest and most persistent questions about quantum entanglement is, can we make use of it to send information somehow? Now, we've already answered this essentially and said no, you can't. But to investigate it a little bit deeper, let's consider a hypothetical experiment. Let's start by preparing a two-particle entangled state, like this one. I've shifted notation a little bit here. Since we're doing quantum information now, I'm referring to the states of our particles as 1 and 0 instead of spin up or spin down or positive and minus. And that's because in computation, that's how we encode information, as strings of 1s and 0s. But I want to emphasize that I'm not doing anything different here. You can think of a 1 and a 0 being spin up and spin down along some particular basis axis if you'd like. But one advantage of this notation is that we can have quantum states with properties other than spin. We can have other properties that are entangled in a very similar way, and we can use those other properties to encode information and so on. And this notation of 1s and 0s is kind of agnostic to the physical system we're using. What really matters is simply the principle of superposition and the principle of entanglement. Now, as before, let's take this entangled state and let's give one of the particles to Alice and send the other one to Bob. Now let's assume that before all this went down, Alice and Bob met together and schemed up a way for Alice to be able to send information to Bob. To achieve this, they agree on two things. The first is that they will always perform their measurements in a common basis, which means that Bob will always find the opposite of what Alice does. And the second is that if Alice wants to send the message yes, she measures her particle state, and if she wants to send the message no, she doesn't measure it. Now, we already know that this is doomed to failure. Regardless of whether Alice does or doesn't measure her part of the state, Bob will either get a 0 or a 1, and he has no way of knowing whether his 0 or 1 is the opposite of what Alice already found, or simply the random outcome of measuring a state that was still in superposition. Either way, Bob doesn't learn anything about what happened on the other end. He doesn't know whether Alice performed the measurement or not. He might know what the state of the second particle or first particle would be if it was measured or if it is going to be measured later, but he doesn't know whether it was measured, for example. So he doesn't know what happened on the other end. But Alice and Bob are not new at this, and they came up with a third step to this procedure to get around this problem. The problem is that Bob has no way of knowing whether he got a random result or whether he got a determined result because Alice already made her measurement. To get around that, before Bob measures the state of his part of the entangled pair, he duplicates the state. He copies the state of his particle onto 100 other particles. Basically, he takes his particle, puts it in a quantum Xerox machine, feeds through a bunch of other particles, and this Xerox machine copies the state of his original particles onto the new ones that he sends through. And finally, he performs his measurement on his original particle and the 100 duplicates. This skirts the problem, because if Alice has already measured her part of the state, the superposition collapses, and Bob's particle is either in the state 0 or in the state 1. So when Bob copies the state, he ends up with a whole bunch of copies that are all either 0 or they're all 1. When he then measures them, he's going to find that all 101 of them have the same exact result. On the other hand, if Alice has not measured her part of the entangled pair yet, then Bob's particle still exists in a superposition. And so when he copies it, he ends up with 100 copies that are also in superposition. And so when he measures their state, he's going to get a 50-50 split, more or less, between 1 and a 0. This procedure gives Bob the ability to say whether or not Alice has measured her state, no matter how far away Alice is. And even if they arranged it so that in their reference frame, Bob would always perform his measurement a fraction of a second after Alice. This is not just non-local behavior. This allows Alice to send information to Bob instantly over arbitrarily large distances. And that brings with it all the paradoxes that we established occur when such instantaneous or faster than light transfer of information can occur. In the past, every time we've run into an apparent paradox, we've been able to resolve it by thinking about our assumptions. One or more of our assumptions has always been wrong in these circumstances. So what assumption or assumptions are the culprit here? It turns out to be the word copies. One does not simply copy quantum states. This leads us to what's called the Nocloning theorem. This theorem states that it's not possible to create an identical copy of an unknown arbitrary state. We can actually prove this pretty straightforwardly by assuming we can do it and proving that we get nonsensical results. So let's start by considering some arbitrary state A that we want to copy. And let's label the state that we want to copy A onto X. In order to go through with this copy process, we need to do something to these states. We need to interact with them in some capacity. Well, doing something in quantum mechanics corresponds mathematically to a linear operator. So let's define a linear operator C that takes two states A and some template X and returns A and A. We have successfully copied our arbitrary state A onto our other template state X. So now we have two different systems, each in the state A. We've successfully copied A from one system to another and preserved the original. But I want to ensure that our copy operator can do this for any state. So let's define another arbitrary state, B, and let's do the same process. Let's demand that applying our copy operation onto the state B with a template X gives us two systems both in the state B. But now let's repeat this for a third state, and let's make this third state out of A and B. Let's make this new state psi equal to a superposition of the state A with an amplitude lowercase a, and the state B with an amplitude lowercase b. We want to ensure that our copy process works for this state as well as it works for A and B. That means the final state should be two systems both in the state psi. We can express this in terms of A and B as well. But C is a linear operator, so it has to follow the rules of linear operators, and we can re-express psi as a linear combination of A and B. And one of the rules of linear operators is that C of A plus B is equal to C of A plus C of B. Another rule is that we can take out these coefficients, lowercase a and b, from within our linear operator, and then we can apply our two conditions from the first two lines to these two terms, and we find that the copy of our state psi ends up giving us the following. And these two lines are not equal to each other. When we actually apply our copy operation to our state psi expanded out in terms of A and B, we don't get back two independent states psi. We end up with this different entangled pair of states that is not this. That was Alice and Bob's mistake. When they decided that they were going to rely on Bob copying his state before performing his measurement, they assumed that they would be able to do that. They assumed that Bob would be able to make duplicates of his states without knowing what it was. I think this is pretty fascinating. It means Xerox can never make a perfect copy machine. They can never build a copier that perfectly reproduces whatever it is you feed into it without destroying the original. This doesn't mean you can't make copies. If you couldn't make copies, for example, we'd be screwed when it comes to digital information, where we copy things all the time. And yeah, if you recompress files over and over again, you lose information, you lose data. But we make perfect copies of digital files all the time. And the reason we can do that is because there is no general process you can carry out to make a copy of any arbitrary unknown state. But when we make copies of digital files, what we're really doing is we're making copies of the states of the hard drive or solid state disk in which that data is stored. And because those systems are effectively macroscopic, I can measure whether that particular bit is a 1 or a 0 without meaningfully changing it. There will be some slight modification to the state of that part of the hard drive, but not enough to actually flip it from a 1 to a 0, which is really all that matters. So while the resulting physical state of the copy on the hard drive won't be 100% exact on a quantum level to the original state that made up the file we're talking about, in terms of how a computer reads that information, there's no difference. And that means, obviously, digital information works and can be copied, and it doesn't all go to hell. But ultimately, the reason why it works is because we have tolerances. We don't require things to have exact values in order for us to be able to read what we want from it. In the beginning of this video, I said I'd be talking about things that we can do with entanglement, and so far all I've talked about are things that we can't do with entanglement. So let's move on to quantum teleportation, although we're going to have to take a little bit of a detour to get there. If you think back to when we were first introducing the concept of span of individual particles, one of the early things we did was we came up with the idea of a basis set of vectors, or of states, so that we could take a small number of simple states and construct any other arbitrary state just by combining those. So for a spin 1.5 particle, those basis vectors that we usually chose were spin up and spin down in the z direction. But we could also choose, for example, spin up and spin down in the x direction as our basis, or any other arbitrary directions. We can also define a set of basis states for two-particle systems. The simplest is all the combinations of the well-defined spins of both particles. So for example, the state 0, 0, the state 0, 1, 1, 0, and 1, 1. We could construct any two-particle state just by adding these basis states together with varying amplitudes. But when discussing entanglement and entangled states, there's actually a different basis that looks a little bit messier, but that actually makes a lot of our analysis a lot easier. Because each of the four represents one of the four most strongly entangled states possible for two particles. It should be relatively straightforward to see how we could reproduce any one of these states, for example, from some combination of these. If I want to recreate the state 0, 0, I can simply add these two together. The 1's cancel out, and we're left with these. We'd have to renormalize it, right? We'd have to add this plus this, and we'd have to multiply it by 1 over the square root of 2, but we can do that. We can combine these two together to produce this state, and so on for the rest of them. These four basis states are called Bell states after John Bell, the guy who came up with Bell's inequality. He was the first person to really introduce these as a useful set of basis states, which we can use to analyze things in a more concise way. And just like how we could perform a measurement on a single particle in its z plus and z minus basis, we could also perform measurements on a two-particle system in its Bell basis, where the result will be one of these four states. Now we're ready to talk about quantum teleportation itself. First thing we should address is what is actually being teleported. This isn't some kind of Scotty beam me up story, but rather what's being teleported is the state of one system. So if we have Alice and Bob and they share an entangled state, Alice is able to teleport the state of some other particle she has to Bob by interacting it with her own half of their shared entangled system. I've written this entangled state this way just to make it extremely clear what is what, but we are mostly going to work with the shortened notation where we kind of clump all these things together. And while I am color coding things, I'm also going to use these subscripts where the first subscript represents tells us which particle is represented by the first value, and the second one represents the second value. I can also represent this state using our newfound Bell states. In particular, the state that I've written down is the phi plus state, so I can use that notation to represent this nice and concisely. Now let's say that Alice has a third particle, which we'll call C, that's completely independent of the first two. It's not part of this entangled state that Alice and Bob share. But what Alice wants to do is to send the state of C to Bob. The amplitudes alpha and beta of this state C can be any complex number so long as their magnitude squared add up to 1, satisfying the normalization condition. But to keep things simple, let's just assume that alpha and beta are positive real numbers. They don't have to be, but it keeps things a little bit simpler and it makes it a little bit easier to understand. The next step is to write down the wave function for the three-particle system of particle A, B, and C. And even though particle C is independent of the entangled pair A, B, we can still write it as a three-part system. It just means that C is not entangled with either of these two. We've already written down states that didn't exhibit entanglement before, and so we can do that here as well. Also pay attention to the fact that I'm putting particle C first in this, and you'll see why I'm doing that in a little bit. If we expand out both of these wave functions, we get a little bit of a mess. And if we multiply this all out, we end up with 4 terms. And what I've done here is I've grouped together Alice's particle C and her particle A. This state is exactly the same as all the states written over here. All I've done is I've simply regrouped the terms. I haven't actually changed anything. And the reason why I've done this is because I want to express the combination of particle C's and particles A's states in terms of our Bell states from just a moment ago. To do so, we can just reverse engineer, for example, the state 0, 0 from these two Bell states by adding them together. We can reverse engineer 0, 1 by combining these two states together, and so on. And when we do so, we arrive at the following three-particle state. Now, it might seem at first like we've just made our lives harder. We turned 4 terms that, it's pretty easy to see what's going on here, relatively speaking, into 8 terms, and we're also operating in a basis that's just a little bit more confusing since these represent superpositions of states instead of nice simple states like 0, 1 and 0, 0. But what we're going to do now is have Alice perform a measurement in the Bell basis on her two-particle system of C and A. And when you make a measurement in a particular basis, the outcome is one of those basis vectors. So when Alice performs this measurement in the Bell basis, her two-particle system will collapse into either phi plus, phi minus, psi plus, or psi minus. But once that state collapses, for example, let's say Alice finds that her two-particle state is in the phi plus state. That means Bob's particle is now in this state. Bob's particle is no longer entangled. By performing that measurement, Alice has broken the entanglement between her particle A and Bob's particle B. She's shifted the entanglement from being between A and B to being between C and A instead. And now, particle B that Bob is measuring, the state that it ends up in depends on these amplitudes, alpha and beta, which started out as the amplitudes of the state that Alice wanted to send to Bob. Let's write out these 4 possible outcomes of Alice's local measurement on the 2 particles in her possession, Ca, in a clearer way so we can more easily see what's going on. So at the top here, we have the state that Alice wants to transmit to Bob, or alternatively, the information she wants to give to Bob, alpha and beta, which can be just numbers. It could be zeros and ones, or it could be, 1 over square root of 2 each, or something like that. And at the bottom, we have each of the 4 possible outcomes of our 3-particle system after Alice performs her measurement on particles C and A, collapsing them into one of these 4 2-particle states. Now, Alice hasn't necessarily yet teleported the state of particle C to Bob, because right now that's only true in this first scenario. If 1/4 of the time Alice would expect to collapse it to this, in which case Bob immediately gets the state that she wanted him to get. But there's a 75% chance that doesn't happen. So we're not done yet. There's more work to be done. Likewise, if Bob performs a measurement at this point, he still has no idea what's going on. He's going to get either a 0 or a 1. He doesn't know if he got a 0 or a 1 because of random chance or because Alice did something, or who knows. In order to complete this process, Alice and Bob have to just get on the phone with each other, or send each other an email or snail mail or something. We already established that quantum entanglement cannot be used to transmit information from one place to another. That hasn't changed. there needs to be some classical component of communication between the two of them. Classical doesn't necessarily mean it has to be like large scale, it just means it can't rely on quantum entanglement in this context. And any such form of communication is inevitably going to occur at speeds less than or equal to the speed of light. But here's the thing. You might say, well, if Alice just has to get on the phone with Bob anyways, why doesn't she just tell him the information she wanted him to have? Why does she have to go through this whole rigmarole? There are two reasons for this. One is the only thing Alice needs to tell Bob is which one of these states she got. And if they have some kind of convention between them, she can literally just get on the phone and say 1. That's all the information she needs to give him for Bob to know exactly what's going on. If he knows that Alice measured 1, that means Bob knows that his state is the state Alice wanted him to have. If she told him 2, 3, or 4, then he knows exactly how it's mixed up from what she wanted. And he could perform a series of operations using quantum logic gates to actually transform any one of these states into the state that we're looking for over here. This is useful because using a single bit of information, literally just sending Bob the number 1 or 2 or 3 or whatever, is enough for Bob to reconstruct the entire state. Bob gets more information than Alice gave him. Because once he has this piece of the puzzle from Alice, he can reconstruct the rest of the puzzle from his particle's state, which was affected by Alice's measurement of particle A and particle C on the other end. Alice's measurement of particles A and C broke the entanglement between particles A and B, entangled A and C, and shifted the state of C over to particle B. I want to emphasize that still no information was transmitted at speeds greater than the speed of light. Bob's state was affected non-locally by something Alice did, but in a way completely undiscoverable to him. Alice then gave him a very small amount of information that actually provides Bob with much more information than you'd expect. In other words, this can be used as a form of data compression. But that's really not what makes this useful. Turns out the most efficient way you can use this to compress information, to compress data, is to get an extra square root of 2 out of it. If Alice transmits Bob 2 bits of information, Bob can extract, at most, 2 times the square root of 2 bits of information. That's not insignificant, but we have way more efficient methods of data compression to begin with. Now, in principle, you could combine this with those and make it even better, but constructing entangled states is really hard, and keeping them entangled over large distances is even harder. So it's really not a big enough difference to be worth the hassle of doing it. There is a much more useful application, though, and it's in cryptography. Consider the following scenario. Imagine that Alice gets Bob a birthday present, and she decides to ship it to him in her suitcase. She wants to be absolutely sure that Bob gets his present, so she locks her luggage with the combination 1, 2, 3, 4, 5, of course. And she decides she's going to send the combination to Bob in a way that can't be intercepted. Well, phone lines can be tapped, emails can be intercepted, mail can be read. So how's she going to do it? Well, she already has this whole system of sharing entangled particles with Bob set up, so she figures she may as well use that. And so the number 1, 2, 3, 4, 5 can be expressed in binary as the following string of 1s and 0s. And she realizes that she can encode this string of 1s and 0s into a series of different quantum states psi. So for example, if she wants to send the number 1, she can make beta equal to 1 so that the state is in the state 1. And if she wants to send the number 0, she makes alpha 1 so that she transmits the state 0. In other words, if she transmits 14 different states, the first one being the state 1, the second one being the state 1, the third being 0, fourth being 0, fifth 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, by setting either beta to 1 or alpha to 1 and the other 0, she can then do what we just described earlier, transmit each of those states to Bob, and Bob can then measure the outcome. So let's see how that would work, for example, for the first digit, 1. Alice would prepare a state where alpha is equal to 0 and beta is equal to 1. Alice then performs her measurement on her two particles, entangling them together and teleporting some element of state C over to Bob. And let's say, for example, that Alice finds the third state. She gets on the phone and she tells Bob, I got this. I measured psi plus. And Bob says, okay. That means Bob knows that his particle is now in the state alpha 1 plus beta 0. Well, alpha was 0 and beta was 1, which means that Bob's state is really just 0. And since Bob knows that Alice is only transmitting zeros and ones, that the fact that he measured the state 0 was not a coincidence. He knows that whatever state he measured was the only state he could have measured because the other had an amplitude of 0. So he knows that he measured 0, which means beta was 1. And he knows that beta corresponds to Alice sending the number 1. So Bob records the number 1. And now they repeat it. Alice once again prepares a state, and once again she wants to send the number 1, so she sets beta equal to 1 so that she's transmitting the state 1. And let's say that this time Alice performs her measurement and she finds the second possibility. Once again, she gets on the phone, she tells Bob, I got number 2. So this time Bob says, okay, that means I know that my state looks like this. Once again, alpha is 0 and beta is 1. So while he doesn't actually know it yet, his particle is in the state 1. When Bob performs his measurement, he finds it in the state 1, or in the state minus 1 technically, but whatever. But he knows that in possibility number 2, state 1 corresponds to beta being 1. And once again, he knows that when beta is 1, Alice is sending the number 1. So Bob records another 1. Note that Alice transmitted the same number twice, but the first time Bob measured a 0, and that meant Alice sent a 1. And he knew it did because he knew we were talking about this state because Alice told him number 3. And the second time we're talking about state number 2, he measured his state in the 1 state, which means, again, he could look at this little cheat sheet and say, okay, well, I know that since I got 1, that means beta was 1. If Alice had not got on the phone to tell him the first time 3 and the second time 2, Bob would have no idea what to do with these zeros and ones. But knowing which of these outcomes it is tells him. However, Alice getting on the phone and telling him, oh, I got option number 3, doesn't tell Bob anything either. Because if Alice measured this, Bob knows he could, in principle, get a 1 or a 0, depending on whether Alice transmitted alpha is 0 and beta is 1 or the other way around. In order to extract the information, Bob needs the information from Alice about which state she found her two particles in, and he needs to perform a measurement on his own state, and between those two things, he can reconstruct the number that Alice wanted to send him. So, for example, if someone had tapped their phone call when Alice was telling Bob which outcomes she measured on her end, the person listening to the phone call doesn't get any information. The person listening to the phone call knows what measurement Bob should make, but doesn't know what the result is. And without that result, they don't know whether each number was a 1 or a 0. And there are 16,384 different combinations of 1s and 0s that are 14 numbers long. Listening into the phone call tells them nothing. Likewise, if someone intercepted particle B on its way to Bob, if they weren't also on the phone call with Alice, then they would have no idea what their measurements of this particle would mean. For example, let's say they measure the state 1. Well, that could mean either beta is 1, or it could mean alpha is 1. So they have no information. The only way to extract information here is to both be on the phone call with Alice and measure the previously entangled state with Alice's particle A. So Alice and Bob could then repeat this process another 12 times, and Bob can recover the remaining 12 digits of the binary number. He can then do a little bit of math and convert it into decimal, and now he knows that the code to the luggage for him to retrieve his present is 12345. This is literally the most basic form of quantum encryption. There are much more sophisticated methods, and even only slightly more sophisticated methods. If Alice and Bob mix it up a little bit, where sometimes Bob measures things in a different basis, they can actually do it in such a way that if someone is listening in on the phone call and somehow has access to Bob's entangled particle, Bob can actually tell if someone else is measuring his particle state. So if Alice's rival Eve is eavesdropping on them, even if she has access to the phone call and the entangled state, if Alice and Bob are just a little bit cleverer than this, they can set it up so that Bob will know whether or not Eve is trying to intercept the passcode to his birthday present. The last thing I want to talk about, and this is going to be really short, is quantum computing in general. I don't know very much about quantum computing, and it's a subject that gets very complicated very quickly. So this is going to be a very, very simplistic overview intended to give you a general idea that's not necessarily entirely technically accurate. The very rough idea is that we can make use of quantum superposition in order to kind of perform many calculations or procedures simultaneously. Classically, if you want to do a series of calculations, you have to do them one after the other. You have to do each calculation independently. Or you can have multiple cores of a CPU, each kind of doing their own thing independently in parallel. But with quantum computing, you can make use of the superposition properties of the qubits, the particles, the quantum systems making up your computer, in order to simultaneously perform many calculations and then read out the results. There isn't just one form of quantum computing, though. For example, there's one method of quantum computing called quantum annealing, which is essentially the idea that you set up your system very carefully and you provide some kind of external stimulus to it so that the system evolves over time. The wave function changes over time in such a way that essentially the incorrect answers interfere destructively, leaving behind only the answer that you're looking for. Quantum computing is not necessarily inevitably an improvement over classical computing, though. It's really that they have their different strengths. For example, it's been proven that in principle, there is nothing a classical computer can't do that a quantum computer can, and vice versa. The difference is in the amount of time it would take them to do it. For example, factoring large numbers is an extremely time-intensive, computationally intensive process. It's very hard to do classically, and it's actually the basis for a great deal of existing cryptography. I can create a very large number by multiplying together, 37 different two-digit numbers. The resulting number will be ginormous. It's really easy to calculate it, but if I just gave you that really big number, it would take you a really long time to find the factors. And so what we can do is you can set something up so that you encrypt data using that really big number. And unless you know how to factor that really big number, you don't know how to decrypt the information. Well, quantum computers are really good at factoring. There are quantum algorithms for factoring large numbers exponentially faster than a classical computer could ever do it, to the point where it would take our best supercomputer, the age of the universe, to crack a decent 256-bit encryption key. It's simply not practical. I actually, to be honest, I made that number up, but I do know it is an enormously big number, and it's just, you can't brute force in practice a large encryption key using classical computing. A quantum computer, however, can do it much faster. That said, if you make the key big enough, if you make it enough digits, if you make the number big enough, just because a quantum computer can do it exponentially faster than a classical one doesn't mean it can do it on a time scale that's useful. If it takes you 1,000 years to crack somebody's password, chances are you're not going to care by the time the algorithm finishes. Another arena where quantum computing could be really helpful is in simulating quantum systems. We can simulate quantum systems using classical computers, but it's intensive. It's not very efficient because you have to simulate all these different amplitudes and superposition, what happens during these measurements and they collapse. There's a lot to keep track of, which in a quantum computer would be done automatically through the actual quantum processes. If we ever become good enough at building and maintaining quantum computers for them to make their way into a typical commercial computer, I'm sure there will be plenty of applications for them to speed up a lot of our computing. But you're never going to take your classical computer and throw it away and replace it with a purely quantum computer. What you would do is you would use both systems, and you would use each system where it is most efficient.